Okay, so good day everyone. So we are now into our examples, guys, for singly reinforced beams, specifically for rectangular beams. Okay, so example 1. So determine the design moment capacity VMN using NSCP 2001 and NSCP 2010 specifications given the following properties. So the beam sections carry an ultimate moment mu of 215 kilonewton meter, then determine whether it is safe or not. Okay, so let us first solve problem A with given with B, which is equal to 300 mm, then total height of 500 mm, then D is 437.5 mm. Then with AS is for 25 mm single layer. Then FC is 21 MPa. Then FY is 345 MPa. Okay. So now, so let me draw, guys, the let me draw it now. A. Then we have title okay. Then we have this one here for 25 mm diameter bars. Then we have H, which is 500 mm. Then we have 300 mm here. Then our depth, effective depth, is 437.5 mm. Okay, so let me read now. Okay, so that is for A. Then we have A prime C, so 21 MPa. Then we have Fy is 345 MPa. Okay, so now let us solve this problem. So for the first procedure, as discussed last time, okay, I'll be solving this problem, guys, using NSCP 2010 alone. Okay, so solving it in NSCP 2001 will be your task. Okay, so do not worry, because the answer or the VMN that you will be getting is the same. Okay, so the only thing that that varies is the procedure and some requirements that you need to meet. Okay, so for NSCP 2010, first you need to calculate the values of A and C. Okay, so let me solve that one. Okay, so in order to solve that, so you already know that the C is equal to T, or the compression force due to the compression block at the compression section, is equal to the tensile force generated by the steel bars. Okay, so we have this C is 0.85 F prime C AB is equal to AS times Fy. Okay, so we have 0.85 F prime C, or should I say so 0.85 F prime C AB. So we have 0.85 F prime C, which is 21, times A, then B is 300 mm, then which is equal to pi over 4 d squared times 4. Okay, so since we have 4 bars, then Fy is 345. Okay, so therefore A is equal to, I think this is 126, no, 126.5 mm. Okay, so this is our value of A. No, again we assume it that the beam is yielding, okay, or the steel bar is yielding. Now since we are utilizing a yield strength here, which is Fy, okay, for the calculation of A, okay. So later we will know if it really if it really yielded, or it does not yield, okay. So beta is equal to 0.85. Why is it that it is 0.85? Since our F prime C is equal to 21 MPa, and this is less than 28 MPa. At the same time, this is greater than 17 MPa. Okay, so again, my solution, okay, so my solution is NACP 2010. Okay, CP 2010 for your reference. Okay, so C is equal to A over beta 1, okay, which is 126.5 over 0.85. So therefore C is 148.824 mm. Okay, that will be the value for our C. Okay, so we already get the value of A and C, so we got it already. So let's proceed to step 2, so which is to calculate the value of the strain at the tension steel, or we'll be getting the strain T, okay, using that formula there. Okay, so going back, so we have strain T. Okay, so strain T is equal to 0.003 then times D minus C, then over C. So this is equal to 0.003. Take note, this is dt, okay, that is dt to be specific, because since the D and dt is not the same if the layer of your steel bar is more than 1, no. So D and dt is the same if you have a single layer bar, no, for your reinforcement, specifically for longitudinal bars. Okay, then we have dt, it is given already, so which is 437. Okay, so 437.5, then minus C, 148.824, then all over 148.824. Okay, so therefore strain T is equal to 0.005882. okay, so that will be your strain T. So by getting strain T, so we need to know the ductility requirement, no, of our beam, okay, by knowing this one here. Okay, so our ET is greater than, I think that is greater than 0.004. So therefore the ductility requirement provided in this section, so the beam may be used. Okay, so let me do it there. Okay, ductility requirement, so this is greater than 0.004. so therefore the beam, so what is the conclusion there? Beam may be used. Okay, the beam may be used. Okay, again, because that is ductile, no? Or you may say therefore that is okay in ductility requirement, no, ductility requirement. Okay, so with that value there, no, for for strain T. Then next is we should know if it is tension controlled, transition region, or in compression controlled. No, for this matter here. Okay, for the three conditions. Okay, so the baseline is 0.005. So I think that is more than, no, or that is greater than 0.005. Okay, so let me draw this one. So this is greater than 0.005. So therefore this is tension controlled. Okay, so tension controlled. So now, so since that is tension controlled, so we may now proceed to our last step, which is to calculate the reduction factor. So since that is tension controlled, okay, and at the same time, guys, you also try to calculate, no? So also try to calculate, guys. Also try to calculate strain. I think you need to calculate as well strain Y. Okay, so strain Y is Fy. I think that is Fy. Okay, this is Fy over Es, wherein this is 345, then over 200 times 10 raised to 3, or 200,000. So this is equal to 0.0017. Okay, so therefore strain T, no, is also greater than strain Y. So this is also one of the indicator that our beam that our steel bar yielded. Okay, so therefore our assumption there is correct for letter A. Okay, or this one, no, so our assumption here is correct. Okay, so since strain T is greater than strain Y. Okay, so now let's proceed to our step 3 to calculate the reduction factor. Okay, so our reduction factor here, okay, so therefore, okay, let me just continue it here, guys. In our tension control, no, since it is tension controlled, then our reduction factor would be equal to 0.9. Okay, so see, we all know already that one, no, last time as we draw that diagram, that is strain T versus P, okay, P factor, wherein the graph is, I think that is the I think this is this one here. Okay, then everything that is going to this portion is tension controlled, and phi there is 0.9. So just review our previous discussion about reduction factor. Okay, that is for strain 4. Okay, so after that, so calculate the ultimate capacity. Okay, you may solve it using this one, or you may also use that one. So there's no any problem. So PMN is equal to P 0.85 F prime C AB, then times D minus A over 2. Okay, so wherein phi is 0.9, okay, so this is 0.9, then times 0.85 F prime C, then times A, which is 126.5, then times B, which equal to 300 times D, 437.5, then minus A, 126.5 over 2. Okay, so just divide it. Okay, so divide it with 1000 squared, so you will be getting a VMN which is equal to 228.168 kilonewton. Okay, the unit will be kilonewton meter, in this case. Okay, so this is the ultimate moment capacity of the beam, and definitely this is greater than your MU, which is given, which is equal to 215 kilonewton meter. So therefore this is safe. Okay, now this is safe in terms of bending. Okay, so that is greater than MU, so therefore that is safe in accordance with this one here. Okay, so with the given MU. Okay, so that is for our first problem for letter A. Okay, so now let's proceed to letter B. With width is equal to 350 mm, then height is 500 mm, then D is 434, then AS is 432 mm, single layer, then same F'C and Fy with our problem A. Okay, so let me draw again that one for our solution. Okay, so for letter B. Okay, so this is our beam now. So we have 432 mm diameter, then we have 500 mm, so we have 350 mm here, then this one here is 434 mm, then F'C is 21 MPa, then Fy is 345 MPa. Okay, so again, so going back to the steps for NECP. This is NECP 2010. Okay, so calculate A. So we have again that one, C is equal to that is C is equal to T, which is 0.85. F'C AB is equal to AS Fy, then we have A, which is equal to pi over 4 D squared, 32 mm, times 4, then times 345 Fy, then all over 0.85 F'C, which is 21, then B is 350. Okay, therefore A is 177.65 mm. Okay, for letter A, or for A rather, compression block. Okay, then proceed to solving C, which is equal to A over beta 1, which is equal to 177.65 over 0.85. So again, I explained already earlier, why is it that beta is 0.85. Then C now is equal to 209. Right? So 209 mm. So this is a distance, distance from the compression fiber, extreme compression fiber, to the neutral axis, neutral axis of the beam. Okay, so now we already know the value of A and C. Then let's proceed to the second step, which is to calculate strain T, which is equal to 0.003, then times 434, this is D, minus C, 209, then all over C, which is 209 again. So this is greater than okay, so this is greater than 0.00332. Okay, so again, we should know if it passes the ductility requirement. Okay, so this is, I think this is less than 0.004. Okay, so therefore the beam can't be used. So actually, guys, if your result is the beam can't be used, so you may stop there if it's really a design, if it's really an actual design. Okay, it's really an actual design. But since in this case we are just solving a particular problem wherein we are tasked to know the moment capacity of this beam, this drawing here. Okay, the drawing of the beam or the properties of this beam with this particular dimension, with this particular bars, with this particular F prime C and Fy. Okay, so even though the conclusion here is the beam can't be used, so you may proceed to finding out what would be the kind of condition it is, either it is tension controlled, compression, or transition region. But in actual situation, when it doesn't pass the ductility requirement, then maybe you need to vary some of the properties of your beam. Okay, so you may vary, say the height, you may increase the height, or you may add up some bars to it. You may also increase the properties of your concrete or your steel bar in order for it to pass the ductility requirement. Okay, so in this case we will proceed in getting what would be the condition of the beam in order for us to know what is the capacity of that beam. Okay, so now let me solve strain Y. So again, that is Fy over Es. I think we have resolved with strain Y already, since they have the same property. So I think this is the strain Y, 0.0017. Okay, 0.0017. Okay, and our strain T is greater than Fy. So therefore it yielded none. So therefore maybe we could use Fy. So therefore our assumption here, or the value of A and the value of C is valid. Okay, since again strain T is greater than strain Y, so therefore using Fy here is valid. Okay, then now it is obvious that this is greater than 0.005. But I think so we may conclude here. Okay, this one. Okay, we'll use this color. So therefore strain T Okay, strain T is greater than strain Y but less than 0.005. Okay, so therefore this is based on our handouts and with the code. So I think this one here, okay, strain T is greater than strain Y but less than 0.005. So therefore the condition is transition region. Okay, so this is transition region. Okay, so if this is transition region, then we need to know, okay, so we need to know the value of phi. Okay, so I derived it last time, no, for the value of phi. Okay, so again, take note that our Fy, okay, take note that our Fy is not a grade 60. Now this is not grade 60, guys, no, because a grade 60, okay, so I think grade 60 is equal to 414 MPa, okay, in SI, since this is 60 KSI, I think. Okay, so this is Fy. Okay, so we derived last time on how to get the value of P if the bar is non-pre-stressing steel and the bar is not a grade 60, no, not a grade 60 bar. Okay, so that is P is equal to 0.65 then plus 0.25, then we have strain T minus strain Y, then over this is 0.005, then minus strain Y. Okay, so this is equal to 0.65 then plus 0.25, then ET 0.0032 minus Y 0.0017, then all over 0.005, then minus 0.0017. Okay, so therefore our phi is 0.764. Okay, so this is greater than, this is greater than 0.65, which is the baseline, no, or the upper limit for, or the limit, no, for the value of P. Okay, so this is good. So we have the reduction factor already, therefore we may not proceed in getting, okay, so in getting the value of PMN. Okay, so we have PMN is equal to phi 0.85 F prime C AB then times D minus A over 2. Okay, then this is equal to 0.764 then times 0.85 F prime C then times A. So it's the value of our A. Our A is 177.65, 177.65. Then we have B, which is 350. Okay, 350. And then we have D, 434 minus A, 177.65 over 2. Then all over 1000 squared. Okay, now therefore VMN, okay, so VMN is equal to 292.69 kilonewton meter. Okay, so this is greater than, no, so this is the answer now. This is greater than your MU, which is 215 kilonewton meter. therefore this is safe. Okay, so this is safe. Again, the only problem for this beam is that it didn't meet the requirement for ductility. Okay, so even though it has a high bearing, or rather bending, so even though it has a high bending capacity, but it didn't meet the ductility requirement, so there might be a problem later uh, in the performance of the beam, or the way it performs during loading. It might be brittle later. Okay, so I think in order for it to be safe, to be safe in all aspects, then I think we should meet the ductility requirement as well, aside from meeting the given mu to the problem. Okay, so I think that's all for problem A and problem B. So stay tuned, guys, for more examples.